You're on.
Good evening, everyone. My name is Jordan Mingo, and I'm participating in Challenge 2016. Now, tonight, we're going to tell you how to find the area enclosed by the ellipse a squared over x squared over a squared plus y squared over b squared equal to 1. So this is the standard equation for every ellipse. So right over here, you can see, so the bounds of a, negative a to a are the major axis, and the bounds from b to negative b are the minor axis. So to solve this, we first need to find y out of this equation. So what we can do is make y squared over b squared equal to 1 minus x squared over a squared. And then we want to distribute b squared over to both sides by multiplying it. So we get y squared equals b squared minus b squared x squared over a squared. So then we want to take the square root of all sides. So we get our final equation of y equals the square root of b squared minus b squared x squared over a squared. Now, the thing that we can do is we can integrate this function. So we have so what we're going to do is we're going to take the quarter area of this. So we're going to do the bounds from 0 to positive a. So our integral will be 0 to a of the square root of b squared minus b squared x squared over a squared dx. Now what we want to do to solve this equation, since this is a trig identity, so what we want to do is we want to make a right triangle, and we want to find the opposite, adjacent, and hypotenuse sides in regards to theta. So what we do is we take this here, we make it equal, we square it, and then we take what's inside here, which would be bx of a, we square that, and then we square this b squared inside of here. So what this will give you is you'll basically have the square root, basically have b squared minus b squared x squared over a squared plus b squared x squared over a squared. So these expressions right here will cancel out. So you'll just be left with b squared equals b squared, and that means b squared is the hypotenuse right here, and bx of a and this square root will be under here. So what we can do now is we need to solve for this, and we need to find x, so we can also get dx. So we can plug this back into the integral using theta. So what we find is sine of theta is equal to bx over a over b squared. So what you'll get for x is a over b cubed sine theta, and dx is just the derivative of that, so you get a over b cubed cosine theta d theta. Now the next thing you want to do is you want to find what this equals. So we know that cosine theta is just the adjacent over the hypotenuse, so we get this square root over b squared, and when we multiply both sides by b squared, we get b squared cosine theta is equal to the square root of b squared minus bx over a squared. So now that we have our expression for this in terms of theta, and our x and dx in terms of theta, we can plug that back into our integral with new bounds of 0 to pi over 2. So our new integral is 0 to pi over 2 of b squared cosine theta times a over b squared cosine theta d theta. So we can simplify this, and this will just become ab cosine squared theta d theta. So with a little bit more simplification, we know that cosine squared theta is 1 plus cosine 2 theta over 2. So we can distribute this ab across the board, so it will be ab over 2 plus ab over 2 cosine 2 theta d theta. So when we integrate this, we'll get ab over 2 theta plus ab over 4 sine of 2 theta from 0 to pi over 2. Now when you do this when you distribute these out like this AB over 4 sine theta will be equal to 0 because we know sine of theta equals 0, and we know sine of 0 equals 0 as well. So this will cancel out and that'll be gone. So what we're going to be left with is AB over 2 times pi over 2, which is equal to pi AB over 4. Now this 4 here is here because we found a quarter of the area, that is the top half of the bounds from 0 to a, or in terms of theta, 0 to pi over 2. So to find the area of the ellipse, we just multiply what we found here from the integral by 4. And thus the area of the ellipse is pi times AB. And that has been the area of an ellipse. This has been Jordan Mingos, and I'm signing off. See you next time.